Hello, we are Team F2 here to walk you through the rainwater harvesting system we designed for Van Anda, BC. Our design process followed 5 key steps: problem understanding, where we researched and contextualized our project; stakeholder analysis, where we analyzed satisfaction criteria; spreadsheet model development, where we developed a focused virtual prototype to model a rainwater harvesting system over 5 years; model testing, where we attempted to optimize satisfaction; and finally, rainwater harvesting system implementation, where we finalized our design choice. Now, to briefly orient you to our project, our goal was to design a rainwater harvesting system capable of providing safe, sustainable drinking water to a 2-person household in Van Anda, BC. You can see on the right that Van Anda is a remote community requiring ferry access to the nearest community. Shipping water like this is unsustainable, and our goal was to design a system that meets water demand for Van Anda residents. From stakeholder interviews, we translated needs into 8 measurable quantities: consumption, which refers to water our system is capable of supplying daily to users; relative cost, which measures our system cost versus a baseline of around $110,000; maintenance occurrences, which account for replacement and cleaning maintenance; on-demand flow rate, which is the flow rate to house taps; reliability, which is how many days our system actually provides the promised consumption; land use, which measures the rainwater harvesting system footprint and land impact; risk exposure, which measures the risk to the health and environment of Van Anda, as well as greenhouse gas emissions released by our power system. These are the weights associated with the satisfaction criteria. As you can see, cost and maintenance are the most important to our stakeholders, followed by flow rate, land use, and consumption, with the rest of the criteria trailing behind. In designing our spreadsheet model, we decided to split the rainwater harvesting system into 3 subsystems. The first subsystem was the daily rainfall model, which incorporated yearly rainfall data, the catchment tank, and storage tank. The second subsystem we developed was a disinfection system, and the third was the power system. In developing these subsystems, our strategy relied on using place order values where they depended on each other. This way, we were able to develop these 3 subsystems in parallel. Our daily rainfall model was used to simulate how much water was collected by the catchment tank and then pumped to the storage tank, keeping track of water in the storage tank as it drops with household use. We found that it is difficult to reliably provide enough water every day, especially during the summer months. As you can see on the right, there are often many days with 0 rainfall in the summer. Through testing, we found that the following parameters to be the best at managing water storage: a 2,500 liter catchment tank with full roof catchment area, and a 36,000 liter storage tank, a distance of 13 meters from the house. Our approach assumed that this distance is the length of the pipe. However, in reality, it would differ by a little bit. This subsystem stimulates the energy requirements of different systems, as well as their associated risks and maintenance operations. We found that chlorine seemed to be unviable due to its high maintenance occurrences. Additionally, the 50-watt UV lamp performed the best since it allowed the highest flow rate. The power subsystem relied extensively on place order values since it is dependent on many factors. However, we found that solar panels are best with a stable energy demand. When there's variation, a diesel generator performs better, albeit with higher costs. Additionally, we found that Pump A, of the 3 pumps available, performed best due to its low cost and high efficiency. We did not account for rain dependency of solar panels, which is a limitation in our approach. However, we did use average sunlight each month, which should give us an accurate result. While we had these subsystems, it was impossible to know whether our findings accurately reflected reality if we considered them in isolation. So, we incorporated them all into one spreadsheet, feeding their outputs into a satisfaction calculator, giving us our complete rainwater harvesting system model. Here you can see an image of our final model. Items in red were parameters we had to choose. Changing them automatically updated the total satisfaction. To avoid fixation, our approach consisted of each team member individually testing different parameters to find the highest satisfaction. While we were doing this, we also tested our results with different rainfall data sets, which you will see in more detail later. After we did manual testing, we found some parameters that simply did not perform as well as others. For instance, chlorine was simply not viable according to our tests. After narrowing down our options, we developed an automated system with Python which tested different combinations to maximize satisfaction. These are some of the examples of the results from our automated testing. After about 150 tests, we got the system on the left, and after 5,000 tests, we got the one on the right, which only increased the satisfaction by 0.01% compared to our manual testing. This helped confirm that our results from before were accurate and close to a global maximum of satisfaction. Here are our final results after testing. These parameters proved to maximize satisfaction. Please feel free to pause to go through each parameter in detail. On the right, you can see the final satisfaction scores for a rainwater harvesting system. These results use rainfall data from Station 1, 2014, which is rainfall data that closely resembles that of Van Anda. In total, our satisfaction was around 86%. Our recommended system performs notably well in cost, maintenance, risk, reliability, and consumption. While it does fall short in GHG emissions, the benefits that the other criteria have eliminate any risk of stakeholder dissatisfaction. As mentioned before, we did conduct a resiliency analysis on our system. We used different rainfall data sets, as you can see on the right, and found their corresponding satisfaction scores. Note that the last two datasets are not indicative of conditions in Van Anda, so we only included them for completeness and to illustrate the most extreme circumstances. In calculating our average, we then disregard Station 3 since it is not indicative of typical results. This gives us an average satisfaction of 82%. To summarize in brief words, we have designed a rainwater harvesting system that is economically sustainable and environmentally feasible for the people of Van Anda, BC, and any remote community.